All right, section 5.3. It's all about solving trigonometric functions. The biggest thing that we have to do in every problem is isolate our function. All right, so this is going to be the first step in always solving. Okay, and sometimes that looks like factoring. Sometimes it's taking a square root to solve. Often we have to rewrite everything so it's in terms of one trig function. All right, and then at the end we're going to look at if there's a change in period for sine, cosine, or tangent. All right, so there's a note at the bottom here. When we're solving equations, we want to find all possible solutions. So when we have a periodic function, such as all of our trig functions, right, they're repetitive, there's going to be infinite solutions. That's what we expect to happen. So we need to come up with a way to write our answers with infinite number of solutions. Okay, so a quick review, we're going to recall some general properties. On the left-hand side, you see our main three trig functions. I want to write the domain, range, and the period for each of those. All right. So the domain for sine and cosine, that's just going to be all real numbers. We can plug in any value for our angle, and we'll get out a value which ranges between -1 and 1. Right. Those functions oscillate between -1 and 1. Inclusive, all right? And the period for sine and cosine, they repeat every trip around the unit circle, and one full time around the unit circle is 2 pi. So our period for cosine and sine are 2 pi. Okay, now the difference for tangent. There's certain values that we can't plug in, right? Tangent is sine theta over cosine theta. So we can't plug in cosine theta equal to 0, so our domain is restricted to x cannot be pi over 2 plus n pi. So we can't have any multiple of pi over 2. So pi over 2, 3 pi over 2, 5 pi over 2, etc. Now our range in this case is infinite. The tangent graph starts at a minimum and increases all the way up to a maximum over one full period. And the period is half of sine and cosine. The period is pi. So we'll actually repeat our values one time. If we go around the unit circle a full time, we'll cover 2 different periods of tangent. All right. So a quick sketch. Sine oscillates starting at a 0, approaching its maximum at 1, and then going back to a 0, back to a minima, and then returning to its original point in one full period at 2 pi. So our zeros are at 0, pi, and 2 pi. And we can continue our graph likewise. Now cosine, on the other hand, starts at a maximum of 1. It oscillates from maximum to minimum and back to maximum in a full period of 2 pi. Okay. Tangent, however, we have asymptotes at -pi over 2 and pi over 2, and one full period would be between those asymptotes with a 0 halfway between, an amplitude of 1 and -1, and then a nice curve connecting all 3 of those points. So you can see the range for tangent is all real numbers because we go off to infinity in either direction. That's what the arrow approaching the asymptote represents. Okay, and the last step of review, this I think is most important. Where are these functions positive? So I'll use green for the positive functions. In quadrant 1, sine, cosine, and tangent are all positive. Okay, moving to the left side, the remaining 3 quadrants, only one function is positive in any given one. So I remember all students take calculus. All are positive in quadrant 1. Sine students is positive there, or just remember the y values are positive. And then tangent is positive in quadrant 3. And finally cosine positive in quadrant 4. Okay, that means that the rest of these are negative. Cosine and tangent are negative in 2. Sine and cosine, negative in quadrant 3. Sine and tangent, negative in quadrant 4. That's going to really help us out when we're solving trig functions the rest of this section. So our first example is a pretty easy one. Remember to isolate the trig function, so we have 2 sine of x equal to 1. So we're going to isolate sine of x by dividing by 2, and we get sine of x equals 1/2. Okay, so looking at our unit circle, okay, sine is the y value, so our y value is 1/2 at pi over 6 and 5 pi over 6. So it's super important that we have the unit circle memorized because we're going to be pulling off values, and that should be kind of a natural step. We shouldn't hesitate with that. Okay, so we get x equals pi over 6 and x equals 5 pi over 6, and these are solutions between 0 and 2 pi. Okay, now we want to encompass all possible x values that are solutions to our equation. So let's think about this graphically for 1 second. I'm just going to sketch the sine graph that we sketched in the previous slide. Okay, and that goes on forever. If we are looking at the y value being equal to 1/2, the value of this function is 1/2, well, you see, if we draw a horizontal line, we have a bunch of different points which tell us all these different angles that would make this equation true. All right, so we're going to take into account that we can rotate any number of times around the unit circle. Okay, so we're going to take our period, which is 2 pi, that's 1 full time around, and we'll just add an integer multiple to our answers. So our two solutions are x equals pi over 6 plus 2 pi n, and x equals 5 pi over 6 plus 2 pi n. All right, so n just tells us n, an integer, is a number of rotations. And since these functions have an infinite domain in positive x and negative x, n can be positive or negative. It's just some integer, 1, 2, 3, -1, -2, -3, etc. Okay, so we went through a lot of detail for this first example, but similar process is going to work for other examples. So example 2 says sine of x plus root 2 equals negative sine of x. So I want to, again, start by isolating the trig function. So I'm going to move my sine term to the left-hand side by adding sine of x. And I'm going to move my square root of 2 to the right by subtracting it. And I end up with 2 sine of x equals negative square root of 2. I'm still trying to isolate sine of x, so I divide by 2, and I get sine x equals negative root 2 over 2. So sine is negative in quadrants 3 and 4. Negative root 2 over 2 would be the value at 5 pi over 4 and 7 pi over 4. So we take those answers. We're going to remember that our answers have to be periodic. They have to be including all possible values. So we get x equals 5 pi over 4 plus 2 pi n, and x equals 7 pi over 4 plus 2 pi n. So those are pretty straightforward. They come right from the unit circle, and all you have to do is use one function and isolate it. Example 3, we have tangents squared. So we're still going to isolate the function. In order to do so, we're going to have to take a square root. So first, let's add 1 to both sides. We get 3 tangent squared x equals positive 1. Now we're going to divide by 3 because we're continuing to isolate, and we get tangent squared x equals 1/3. So when we're solving this, we're going to take the square root of both sides. We get tangent of x equals 1 over root 3, which will rationalize. And hopefully now we get tangent of x equals root 3 over 3, which is perfect because that's a unit circle value. So that's unit circle value is at the angle pi over 6, and also at 7 pi over 6. Now there's something that I want us to think about. If our two answers are x equals pi over 6 plus 2 pi n, and x equals 7 pi over 6 plus 2 pi n, well really, because the period of tangent is just pi, what we can do is write both of these answers as one answer, x equals pi over 6 plus pi n, where instead of 2 pi n, we just have pi, since that's our period. Okay, so we're really combining the two answers I wrote in black into one answer that encompasses all of our solutions. Example 4, we're going to try factoring. This is one of our also common methods in solving. So I'm going to start by setting everything equal to 0 so that I can start to factor, because you can't solve a factored expression unless you have it equal to 0. So let's subtract 2 cotangent of x from both sides, and I get cotangent x times cosine squared x, and then minus 2 cotangent x equal to 0. Now I see I have a cotangent x in common, so I'm going to factor that out and collect what I'm left with. I'm left with cosine squared x, and I'm left with a minus 2. All right, so we're going to set each factor equal to 0. So the first one we get is cotangent x equals 0. So this is true since cosine of x over sine of x would have to be 0. That means that it has to be 0 over 1, or 0 over negative 1. All right, so the period of cotangent, just like tangent, is pi. So we're going to take our first answer. When cosine is 0 and sine is 1, that's at the angle pi over 2. So our first answer is x equals pi over 2 plus pi n. Okay? So just a quick sketch of the unit circle to make sure we know where we're at. We're at this vertical line, pi over 2, the point 0, 1. Okay? Now let's solve our other factor set equal to 0. We get cosine squared x minus 2 equals 0. I'm going to add 2 to both sides. So cosine squared equals 2. When I take the square root, I get cosine of x is equal to plus or minus the square root of 2, which is 1.4 approximately. All right, that is out of our range for cosine. It has to be between -1 and 1. So in this case, there is no solution. So our only answer is the one in red, pi over 2 plus pi n. All right, continuing on. Example 5. We're going to also factor this expression. So hopefully we noticed by now this looks like a quadratic. So I'm going to use u substitution. Let's let u equal sine of x. So we end up with 2u squared minus u minus 1 equal to 0. So we're going to factor that 2u plus 1 and u minus 1. Okay? If you're stuck, use the box method or some other method to factor that. But for now, I'm going to keep moving. Once we have our factors, it's as easy as setting each of them equal to 0. So 2u, u is sine theta, or x, sorry, sine x, plus 1 equals 0. And then we also get sine of x minus 1 equals 0. Let's work on the left one first. We're going to subtract 1 and divide by 2, so we get sine of x equals -1/2. So that gives us, based on the unit circle, sine is negative in quadrants 3 and 4, and -1/2 would be at 7 pi over 6 and 11 pi over 6. So I'm going to emphasize the instructions because we kind of skipped over them. We only want to find our answers in the interval 0 to 2 pi. So in this case, all I need to write is x equals 7 pi over 6 and 11 pi over 6. I don't care about the periodic answers in this case. Sometimes we don't ask for all of them just to make it a little bit shorter. So on the right-hand side, I'm going to solve for sine of x. Sine of x equals 1 if I add 1 to both sides. And this is true at x equals pi over 2. So in this case, there's 3 solutions for x that would work out. All right, moving on. We're going to continue to have to factor, but in this case, we have 2 different functions, sine and cosine in our example. So first, let's get everything in terms of one function. So let's get it in terms of cosine in this case. Okay, so we've got 2 times sine squared of x. If I want to turn that into cosine, what I'm going to do is use our Pythagorean identity, 1 minus cosine squared x. I still have my plus 3 cosine x. And let's actually move our 3 over. So let's subtract 3. So minus 3 equals 0. That's going to help us when we have to factor it in a little bit. So I'll distribute my 2. I get 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. Now we're going to put it in standard form where it's ax squared plus bx plus c. So we've got negative 2 cosine squared x plus 3 cosine x. The 2 minus the 3 would give us a negative 1 equals 0. And just to make our lives a little bit easier, let's divide everything by negative 1 so that we have a positive a value. So 2 cosine squared x plus 3 cosine x plus 1 equals 0. Actually, correct that. The middle term should be minus 3 cosine of x. All right, so here's our u substitution. Let u equal cosine x, and we get 2u squared minus 3u plus 1 equal to 0. And again, if you need the box method, that's okay. But hopefully we notice that 2u squared would have to be a 2u and a positive u. Plus 1, it's going to have to be 1 and 1. And our b value of negative 3 is negative, so they're both minus. Okay? If you need box method, that's totally fine. Go right ahead. So we're going to set each of these equal to 0. I'm going to draw my work over to here. So the first one is 2 cosine x minus 1 equals 0. Cosine of x is equal to positive 1/2. And that would give us x equals pi over 3 plus 2 pi n. And x equals to 5 pi over 3. And then our other problem, u minus 1, that's our other factor. So u minus 1 would give us cosine x minus 1 equal to 0. That means cosine of x is equal to 1. That only happens at an angle of 0 radians. So we can write x equals 0 plus 2 pi n. We don't even need the 0, so we'll just write 2 pi n. Okay, so there's our 3 answers boxed out. Example 7, I think, is probably one of the trickiest ones. And we have sine x and we have cosine x, but neither of them are squared. So we have no way to relate sine x to cosine x. So let's try squaring both sides and hope that a Pythagorean identity appears. So let's try squaring both sides. I'm going to start my work way over here on the left side. So cosine of x plus 1 squared equals sine of x squared. All right, set up the problem and I squared both sides. On the left side, I have to FOIL. So I get cosine squared x plus 2 cosine x plus 1. On the right-hand side, I get sine squared x. Now I'm going to turn everything into cosine, just like I did in the previous problem. So I'm going to make the right-hand side 1 minus cosine squared x. The left-hand side can stay the same for now. And now we're just going to move our terms over. So we're going to subtract 1, and we're going to add cosine squared x to both sides. So we get 2 cosine squared x plus 2 cosine x. Our plus 1 and our minus 1 are go away, and we have that equal to 0. So we pull out a common factor of 2 cosine x, which leaves us with a cosine x plus 1 equal to 0. And it goes just like all the other problems. We're going to set each factor equal to 0 and solve them. So our first one, 2 cosine of x equals 0. That means that cosine x equals 0. So that's that x equals pi over 2. And x equals 3 pi over 2. If we have cosine of x plus 1 equal to 0, that means that cosine of x equals negative 1, which happens at x equals pi. So this problem, we're trying to find all answers between 0 and 2 pi. Right? So we have all three answers. The question is, when we squared both sides, it's possible that extra answers appeared. Okay, so this is the only time that you need to check all of your answers by plugging them back in. It's always a good idea to check them, but this time is especially important. So we're going to check pi over 2 first. In our original equation. So that would be cosine of pi over 2 plus 1 is equal to sine of pi over 2. Is this true? Well, cosine of pi over 2 is 0 plus 1 equals 1. Okay, that worked out. Now we'll check 3 pi over 2. So is cosine of 3 pi over 2, that would be 0 plus 1, and the sine of 3 pi over 2 is negative 1. So 1 is not equal to negative 1. We're going to cross off x equals 3 pi over 2. And our final answer we're checking is pi is the cosine of pi plus 1 equal to the sine of pi. Well, negative 1 plus 1, is that equal to 0? Yes, it is. So our two answers are x equals pi over 2 and x equals pi. So if you ever square both sides to solve, it's not a very common technique, but it will help you. Just be cautious that you check your answers. All right, there's 2 more examples left. And these 2 examples are particularly special because no longer is our period the period of our parent function. So sine and cosine aren't going to be a period of 2 pi. Tangent isn't going to be a period of pi anymore because we have some number multiplying our angle. So in this case, we have 2 cosine of 3x minus 1 equals 0. So I still want to isolate the trig function, so I'm going to add 1. And I get 2 cosine 3x equals 1. I'm going to divide by 2. I get cosine of 3x equals 1/2. All right, so we're going to relate this. It's kind of like cosine of t equals 1/2, which we know that would be true at pi over 3 and 5 pi over 3. But instead of our angle being t, our angle is 3x. So we relate this to cosine t equals 1/2, where t would be equal to pi over 3 plus 2 pi n, and t equals 5 pi over 3 plus 2 pi n. But now what I'm going to do is I'm going to erase my t's, and I'm going to switch them for 3x. Because that's really what the angle is, 3x. Now we're trying to solve for x at the end of the day, so I take this full equation, and I get rid of the 3 on the x by multiplying everything by 1/3. So our first answer would be x equals, we distribute the 1/3, we get pi over 9 plus 2 pi over 3n. And our second answer would give us x equals 5 pi over 9 plus 2 pi over 3 times n, times our integer n. So you notice the number multiplying n is exactly what the period is. In this case, the period is shrunk to 2 pi over 3 instead of the usual 2 pi. Okay? And our final example, in this case it's tangent. So our typical period for tangent is pi, but in this case we expect it to be our b value of 4 times pi, so 4 pi. So we'll see what happens when we isolate this function. We'll subtract 3, we get 3 tangent of x over 4 equals -3. We're going to divide both sides by 3 and get tangent of x over 4 equals -1. Okay. Looking at the unit circle, the typical tangent function repeats every pi. So if we cover all the values in quadrants 1 and 2, then these repeat down here in quadrants 3 and 4. So we only need to look at the value when tangent's -1, and that happens to be at the angle of 3 pi over 4. So we can set it up just like the last problem, but instead of x, we have x over 4 is equal to 3 pi over 4 plus pi n. And then to get our x alone, we just take our entire equation and we multiply by 4. So we get x equals 3 pi plus 4 pi n. Okay, so the most important thing, we isolate our trig functions. Sometimes we do that by taking square roots. Sometimes we have to factor. Often if we're given different trig functions in one problem, we have to get everything in terms of one of those trig functions. Be especially cautious with these change in period ones. Sometimes the fractions can get a little bit tricky. So there's 4 examples on your next slide for you to go ahead and try. The first 2 are really short, and the fourth one, that's the one you have to be careful of. Keep in mind that there's a change in the period.